All right, guys, moving on to the next lesson, triangle congruency. And I told you guys last time, this is the main theme of the chapters. Can you recognize congruent triangles when you see them? There's going to be a lot of information here. I'm going to explain why it's true a little bit and then talk about how to recognize it. So those are two different things a little bit. To get a good grade, you just got to be able to recognize when you have congruent triangles. But I'm also going to go into some depth as to, what makes them actually congruent. Why are they congruent? All right, so let's start with what the naming system looks like. So we have SSS. SSS stands for side, side, side. In other words, we have information about three sides of a triangle. So if I draw myself a triangle here, I'm just going to make up some numbers. This side might be 14, this side might be 7, and this side might be 10. And what I'm trying to get you guys to understand is, when do I know triangles are congruent? If I had another triangle that was the exact same information, are they the same triangle? If I gave you instructions and I said, hey man, I need you to build me a triangle. I need it to have side lengths of 7, 10, and 14. How many unique triangles can you make with that information? Well, let's go take a look. We're going to go to my friend GeoGebra here, and I'm actually going to build the triangle. What were the numbers I said? I said 7, 10, and 14. All right, so I'm going to make a triangle with those lengths. So first, I'm going to make the longest one, 14. So right now, if I was at point A and walked to point B, I've walked 14 units. I'll measure it just so you can see it, guarantee it. That is a 14-unit long segment. The other two lengths need to be 7 and 10. I think that's what I said. Yep, 7 and 10. So how am I going to do that? How am I going to pull off 7 and 10? So these are called constructions, sorry. And in constructions, we have a tool called a compass, not a north-south compass, but a geometry compass. And a compass creates circles. And what does that do for us? Well, let me show you. If I create a circle around point A with a radius of 10, what that means is everywhere on that circle is 10 units away from point A. So I could put a point on here. It doesn't matter where it is, right? Every single spot I put point C is 10 units away from A. But we have more restrictions than that. We also need our triangle to have a third side of length 7. So are any of these spots that are 10 away from A, are they also 7 away from B? And that's what we got to figure out here. So let's see. How could we figure that out? Well, I'm going to use the compass again, where I'm going to go over here and I'm going to draw a circle with a radius of 7. And as you can see, there are two spots where the distance is 10 units from A and 7 units from B. So let me draw those segments. If I connect A to C and B to C, and then I'm going to connect A to D and B to D, I'm going to hide these circles so they're not in our way anymore. And what we have here are two triangles that each fit the description that I gave. I said I wanted you to build a triangle that had lengths 10, 7, and 14. Well, both of these triangles have lengths 10, 7, and 14. So then the question is, are those two unique triangles or are they the same triangle? And in order to know that, we would have to know how big the angles are. So I'm going to measure the angles of these triangles. And we will hopefully figure out if they're the same triangle or not. So, I just hit the wrong button. Sorry about that. Wrong one again. Let's go this way. So there's the three angles of the first triangle. And let's measure I keep messing up. A, B, C. Wrong way. C, B, A. It's not liking that. I am just going to not measure that one. Okay, it doesn't matter. So I'm going to measure the angles over here. So B, A, D. Wrong way. D, A, B. Got it. And then the angle at the bottom. See if we can get that. And it's being very... Okay. Woo! I've never had that much trouble before. Not a big deal. All right. So these angles, and if the first two angles match, doesn't it make sense that the third one would have to be a match? So what we know here for sure is that these are the exact same triangle. So this is not two unique triangles. This is the same triangle 2 times. So what did we just prove? I know it might be kind of hard to understand, but what we just proved is if I gave you instructions, instead, build me a triangle that has lengths 10, 7, and 14. If that's all you had to do, there's only one triangle you could build. And that triangle would have angles of 28.1, 109.62, and whatever that third one is. That's the only way you can make that triangle. There's no other way to make that triangle. So every triangle that has those 3 side lengths is going to be congruent to each other. Every single one. So SSS, this is our first triangle congruency postulate. And what it means is if you have, let's draw a couple triangles here. If you have 3 sides of one triangle match 3 sides of a second triangle, then they're the same triangle. These are the same triangle, right? Like if this is 10, then this is 10. Because of the way they're marked. If they're marked the same, then they are the same. If this is my 14, then this is my 14. And if this is my 7, then this is my 7. So are they the same triangle? Yes, they are. Now what you're thinking, they don't look like you put them on the wrong side. I know. I purposely put them on different sides. Guys, we go by what we're told, not by how things look. 1 dash goes with 1 dash. I don't care if that 1 dash and this 1 dash look like they're different sizes. We go by what we're told. So if I call this triangle ABC, call this triangle DEF, those are congruent triangles. How do I know? Because all 3 sides are have a match. This is the SSS triangle postulate. And what it says is if 3 sides of one triangle are congruent to 3 sides of a second triangle, then the 2 triangles are congruent. So we know that triangle ABC is congruent, and this is another thing we have to be able to do. We have to be able to write congruency statements. So what does ABC go with? Well, here's how I figure it out. ABC, if I start at A, go to B, I've crossed through my 1 dash. So that's A to B is a 1 dash, B to C is a 3 dash, and then back to A is a 2. So in order, I hit 1, 3, 2. So if I name the other shape, I need to make sure I'm hitting the same sides in the same order. How could I name this so that I hit a 1, a 3, and a 2 in order? It would have to be FDE. So the corresponding triangle is FDE. So triangle ABC is congruent to triangle FDE. And if you want them to look the same, you can redraw them if you want. They don't look the same, I get it. But those are the corresponding parts. All right, how did we know they're congruent? That is from SSS. So we're going to write proofs on this soon. And if you're telling me triangles are congruent, well, we're about to learn all the ways we can say that. But one of them is SSS, and that's how we knew this one. All right, as a quick little follow-up, do we now know that like angle D is congruent? Here's D. What is D congruent to? B. How did we know that D and B are congruent? And we learned this last time. It's called CPCTC. We got to make sure we say it fast. No slow pokes on that, guys. CPCTC. So what did that mean? That means that the corresponding parts, right? Look at D and B. Are they corresponding parts? Yeah. Of congruent triangles. Are the triangles congruent? Yes. Are congruent themselves. So D and B, they're the corresponding parts of congruent triangles. Therefore, they're congruent. That's what CPCTC means. Corresponding parts of congruent triangles are congruent. Oh, gosh. What am I doing? Oh, dear. Oh. Sorry, I erased too much. Okay. So that's the first one. Let's look at the second one. I'm going to do it in GeoGebra as well. It's called side angle side. So let's say we have a triangle here. So this was 3 S's. This is going to be SAS. So if we're talking about these 2 sides, look at the name. Like this A, it's holding hands with both S's. It's right in between. They're holding hands. La, la, la. The A is called the included angle. A is the included angle. Okay? Looking at the picture, let me label these A, B, and C. What's the included angle? Well, there's a few ways you can tell. If I were to trace the two sides, I know BA, I know CA. If I trace those two sides, I've literally made the included angle. The included angle must touch or hold hands with, right? It's holding hands right here. It must touch or hold hands with both sides. If the name, look at the name, where's the angle? If the angle is between the two sides in the name, then the angle needs to be between the two sides in the picture. It's called the included side. So that is two sides and the included angle. Is this angle up here, is that an included angle? What do you think? Well, if I trace the two sides I'm talking about, no, I didn't make that angle. I made this one. There's only one included angle. So we would call that a non-included angle. There's actually two choices for that. This one's also a non-included angle. So that would be SS, non-included angle. The way it's drawn now would be called SSA. That's two sides and a non-included angle. We're going to get to that later. But the way we want it is SAS. So that's an SAS configuration right there. Now, I'm going to make another version of this triangle. And we're going to we're going to create it in GeoGebra. So let's make up some numbers real quick. Let's say that this side is 10. This side is 8. And we have like a 40-degree angle. All right? If I said, hey, take these measurements and create the triangle for me, how many triangles could you make? If you don't want to see this, you fast forward through the video, it's fine. I'm going to do it real quick, and we're going to see how many triangles we can make. Well, the length of the first segment was 10. So there's a triangle with length 10. Or not a triangle, there's a segment with length 10. Now, we know that we're going to turn, or we're going to have a 40-degree angle, okay? So a 40-degree angle, and it was on the left side. So I'm going to create a 40-degree angle on the left side, touching this 10. Oh, it's already at 40. Nice. And I'm going to connect a line. Now, here's the thing. If I put a point on this line, I don't care where it is, right? Every single one of these spots, wouldn't that still use that 40-degree angle? Now, it can't be over here because that would be the 140 side. We don't want the 140 side. We want the 40 side anywhere. It could go forever. It could be super close. It could be super far. I don't care where it is, right? All of those spots would use that 40-degree angle. But we have a certain distance we want to go. We said the distance needs to be 8. So what I'm going to do is use the compass again, make a circle with a radius of 8. And where does it hit? Well, it hits 2 times. But again, we talked about we don't want this spot. That's not the spot. Yes, that's 8 units away, but that angle would be 140. We want an angle of 40. So that's not the one we're going to hit. We're going to hit this spot. And when we do that, I'm going to hide the circle. So point C is the correct distance. Actually, I'm going to hide one more thing. I'm going to hide that line. Okay. If I draw a segment from A to C, is it the correct length? Yeah, it's 8. Did I make the triangle that we described? Does it have lengths of 10 and 8 with the included angle being 40 degrees? The answer is yes. Well, how many ways can we finish this triangle? There's only one more side to draw, and there's only one way to draw it. Every single triangle that, like if you know 2 sides and the included angle, it's going to be the same triangle. If I said make me a triangle with sides 10 and 8 and an included angle that's 40 degrees, this right here is the only triangle you could make. The third side would have to be 6.44. There's no other way to do it. There's only one line to finish the job. All right, so I've showed you, hey, it's going to be congruent. So over here, let's mark this side up a little bit. So let's say we know, let's change it up. Let's say it's over here, over here, over here. We'll call this one DEF. Let's practice naming it. So is that two sides in the included angle? Is that the same two sides and the same included angle? Yes, they're marked the same way, so they got to be congruent. So we know that triangle ABC is congruent. Well, if I call it ABC, what would the other one have to be called? Let's trace. We go through a double dash, a blank, and a single dash. So what would happen? How do I do double dash, blank, single dash? The only way to accomplish that would be FED. Everyone agree? All right. Now, what would be the reason? Well, that would be side angle side. That's how we knew they were congruent. Could we now say something like BC? What is BC congruent to? We don't even need the picture. BC, what does it correspond to? ED. Does it actually matter what order we write that in? This order matters a lot because it's based on this. But when we're writing the individual segments, could I call it DE? Is that okay? Yeah. Isn't side DE and it'd be like a triple dash? We know those sides have to be equal now. Doesn't matter if you call it DE or ED. And we know that. How? Say it fast. CPCTC. So like this is the kind of thing we'll be doing in proofs here soon. All right. Now, I'm not going to make every single situation. It would take a long time. As a matter of fact, like to make AAS, it's actually a modified ASA. It's the same premise. But I promise you that, actually, I'll make ASA here in a second. You know, you can fast forward it. It's just a video. So if you want to fast forward, you can. I'm going to talk about ASA and AAS right now, though. So if I have a triangle, boom, look at that beautiful triangle on demand. What would AAS look like? Well, now we're talking about two angles, right? Two angles, and where's the side? Is it included? Does the side touch both angles? No, look at the name. It's only holding hands with one angle. So we have, now what about ASA? Now that side is holding hands with two angles. But that's not what we're working with. We're working with AAS. What would that look like? Well, if I had these two angles, I'll call this A, B, and C. Which side are we talking about? It's got to be a non-included side. Well, if you thought it was this one, you thought wrong. If I were to draw that side, did I touch both angles? Yes. That is the included side. That is ASA. We're going to do that in a second. I want a non-included side. And there's actually two choices. It could be this one or it could be this one. Both situations are angle, non-included side. That means if I were to highlight that side, I'm completely avoiding one of the angles. In this case, I'm completely avoiding angle B. If I were to do this side, I'm completely avoiding angle C. Both of them are considered AAS. So if I go back over here, let's say I do the same order just to keep it a little less confusing. That we know is going to be congruent triangles. Now, what if this was the side we knew? Are those the same triangle? This is angle, non-included side. This is angle, non-included side. Are they the same non-included side, though? Think about which angle they're avoiding. Like if I draw this one, I'm avoiding the 2 dash. If I highlight this one, I'm avoiding the 1 dash. They're not the same AAS. So we couldn't say these are congruent. Maybe they are, but we can't confirm that. It's got to be the same AAS. Now we can say that these are congruent. So sometimes, always, or never. Listen carefully. If you have two angles and a non-included side, congruent to two angles and a non-included side, then the triangles are congruent. That answer is sometimes, because they didn't specify which non-included side. So you have basically a 50% chance of it being the same side. That's not always, that's sometimes. All right, so in this one we could say triangle ABC, and these are drawn in the same order. That's nice, right? A to B to C would be just DEF. Nice. So I'm not going to make that one. I'll make this one in GeoGebra here in a second, but let's just talk about what it looks like. So we got triangles. It's called angle, side, angle this time. So angle, which side, if I call this A, B, C, which side is the included side? Look at the side. Where is it? That side is in between both angles. That's called the included side. It would have to be this one. If I were to trace this one, did I avoid either angle? No, I'm holding hands with both angles. Holding hands. We're just having a good old time. So that is the included side. That is an ASA configuration right there. And let's go build one real quick. Let's pretend that this is 10. Let's say we have a 40-degree angle, and then let's do like an 80-degree angle. I don't know, just making something up. So if those are the things that must happen, let's go see if we can build it. Again, if you don't want to see this, fast forward. It's fine. Won't hurt my feelings too much. So I know that I have a length of 10. I got that locked in. Here are the things that have to happen. On the left side, I need a 40-degree angle. So I'm going to do an angle on the left that is 40 degrees. It's already 40. Nice. Oh, I chose poorly. Angle on the left, that's 40 degrees. And then I'm going to choose an angle. I want an angle on the right. Actually, time out. Let's draw a line. So here's what we know. If I'm on AB and I walk any spot on this line would create a 40-degree angle inside that triangle. So it doesn't matter where it is. Any of these spots, we need to figure out where. Here's the thing that we know. The only other thing we know is that the angle on the vertex B has to be 80 degrees. So over here, I'm going to do vertex B. I'm going to make it 80 degrees. And, ooh, I can't see the point. Oh, it's way up there. So if I connect that with a line, A to B, how many spots do they hit? Oh! Just once. So that spot C, let me hide these lines. Let me connect A to C. Nope. Let me connect with a segment, A to C and B to C. This triangle is the only one that exists that has a 10, a 40, and an 80. Those other two sides would have to be this. So if I said, hey, make me a triangle with a 10, a 40, and 80, there's only one spot, right? It has to be 40 degrees. It has to be 80 degrees. Those lines are only going to hit in one spot. And in this case, it was where point C is. It's the only place that makes all those things true. So how many triangles could you make that are 80, 40, and 10? Just one. So that is enough to know that they're the same triangle. So if I call this DEF, and we have boop, 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 are those congruent triangles? Yeah. You better believe it. All right. So HL. What type of triangles? Well, first off, talking about triangles, what do you think H and L stand for? Well, if you guessed hypotenuse and leg, you are correct. Now, what type of triangle has a hypotenuse? The only type that has a hypotenuse is a right triangle. This is for right triangles only. That's it. It's got to be a right triangle. So here's the thing. We have a menu, basically. SSS. So if we go to the congruent triangle store, they're always serving SSS triangles, SAS triangles, AAS triangles, and ASA triangles. They're always serving those. Always on the menu. They're always options. But sometimes you get lucky. Sometimes it's a special day, and they are serving HL. What has to happen for it to be an HL day? You got to be working on a right triangle. Now, don't get confused. Does that mean every single right triangle is an HL situation? No. Not every triangle that has a right angle is automatically HL. So here's a right angle. So I got a right triangle here. is this an HL situation? Do I have the hypotenuse? No. This is just a side angle side. That's two sides in the included angle. Right now, you're looking at SAS. So that's not what we want. What about now? What do we have now? I have angle, angle, side. That's AAS. That's two angles and a non-included side. That's not it. Okay. What if I had this side? Well, what is that? That is side, non-included angle. That's SSA. But we haven't talked about SSA. That's not one of our choices. But is this a hypotenuse and a leg? Yes, it is. That's what HL looks like. HL is very specific. So if you have two triangles that are right triangles and you know that the hypotenuse and the leg matches, that's when you have HL. So it could even look like this. That's still a hypotenuse and a leg matching a hypotenuse and a leg. So let's think about this for a second. What if we knew the hypotenuse was 10 and the leg was 8? Is there a way to know that third side? The answer is yes. You got to hit that Pythag. You could do Pythagorean theorem. Hopefully you know this one. It's one of the most famous ones. It's a 6, 8, 10. Well, if that's 10 and that's 8, that means this is 10 and this is 8. That means this is also 6. So if you know two sides of a right triangle, don't you automatically know the third? Kind of like if you know two angles. Now that only works on right triangles, but yeah. So HL is kind of, in a sense, an SSS situation. Because you know if two sides match, the third one has to match. But we're going to call that HL. So that is hypotenuse leg. All right. So we got a couple more things to go through here. I'm going to create this, but I do want to talk about it first. Side angle. Where's the angle? Two sides. Does the angle touch both sides? No. It's two sides. So let's say it's those two sides. Which angle are we talking about? Well, if you chose this one, wrong. That's side, angle, side. That's two sides and the included angle. That angle touches both sides. I need an angle that doesn't touch both sides. I'm going to choose this one. This is another situation, actually, where you have two options. You could have picked bottom left, but I picked bottom right. That is side, non-included angle. Okay, so we've got side, non-included angle. And actually, I'm going to change it up. I'm going to do this side, and this angle. Okay, I feel better about that. That's a little easier to make in GeoGebra. So I'm going to pretend that this is 10, 8, and 40, just like we did before. Remember for side, angle, side, I did 10, 8, 40. Well, I'm going to do side, angle with 10, 8, 40 as well. So I'm going to construct this. Again, if you don't want to see, it's fine, but I think this might be one of the more important ones to see, just so you can really understand what's going on here. So I have a length of 10. Now, our requirements are an angle of 40 degrees, and the opposite side is 8. Before, it was an angle of 40 degrees, and the adjacent side was 8. We're going to do the opposite side. It's got to be a side angle side situation. So I'm going to make the angle first. And I want it to be a 40-degree angle. 40-degree angle. Hello? My goodness, there we go. 40-degree angle. And I'm going to draw a line connecting those spots. And again, we've talked about this. Every single spot on that line will create a 40-degree angle. It could be super close. It could be super far. The issue is we know the side opposite the 40. So I'm going to use my compass. I'm going to create a circle with a radius of 8 on the other vertex. And what you'll see is that it hits the line twice. There are two spots that fit the requirements. So just so we can see it a little better, let's hide some stuff. All right. So there's a potential triangle that fits all our requirements if I connect A to D and D to B. How do I know? Is that a length of 8? Yes. Does that have 10, 8 with an opposite angle of 40? Is that SSA with 8, 10, 40? Yes, yes, yes. Burn that triangle into your brain. Could I have gone up here? Does that also fit the requirements? Is that still 10, 8, 40? Yes, there are two places that are 8 units from A that still have a 40-degree angle over there, guys. So SSA does not prove congruence. Why not? Because there could be up to 2 triangles. You'll learn a lot more about it in pre-cal. And a lot of the time, there's only 1 triangle. I would even say most of the time, more than half the time, there is only 1 triangle. But would you bet your life on it? If this is all you knew, would you guarantee me those triangles are congruent? And the answer is no. So you would write not enough information. We're not saying they're not congruent. They might be. They probably are. But we can't guarantee it. So it's a better than 50% chance they're the same triangle. But we cannot promise it. So you will never, ever, ever, ever write SSA as an answer. If you ever get the urge to write SSA, you just need to slap yourself. Bad. Don't write it. How could we remember that? I hate to even show you. You've probably never seen or heard of this word before, but those of you that have, you know it's just terrible. If you look at this, SSA, what? Okay. Read it backwards. It's A, S, and then there's another letter I'm not going to write. I can't do it. I get it. Okay. We're not going to write the word. But you should never write it anyway. But don't be writing cuss words all over my papers. So you certainly don't write ASS. SSA is wrong too. The only time you would ever write SSA is if I said which configurations do not prove congruency. SSA is on that list. But you'll never say SSA as an answer. That won't happen. Now, HL looks a lot like SSA. It is side, non-included angle, but the angle is 90. It's a special case. That is going to work. All right, and then AAA, we'll go through this real fast. AAA, angle. What's wrong here? Why does that not prove congruence? Well, it could be giant, it could be tiny, and have the same angles. So how many triangles, if I said, hey, build me a triangle that has like 50, 60, and 70 degrees, how many of them could you do? The answer is infinite. You could build infinite. They could be any size imaginable. So there are infinite choices. So again, if you're thinking AAA, what are you going to write? NEI. Maybe they're the same. They don't have to be the same. So here's a test question. Explain to me why SSA does not prove congruence. Test question. Because it could create up to 2 congruent triangles. So it doesn't prove congruence. How about AAA? Explain to me why that doesn't prove congruence. The best answer is angles don't determine size. The angles don't tell you how big the shape is. There's infinite triangles that can be created. How can we remember that? Well, if I'm standing here, so there I am, and let's say that, I don't know, what is something really scary? Something like, there's like a ghost over here. All right, we got a ghost. If I was walking around and I saw that ghost, what am I going to do? I'm going to go, ah! And I'm going to run away. Guys, if you are thinking of writing this, I want you to go, ah! And run away or write NEI. Let's go. Whew, we feeling pretty good, guys? So, we have 5 methods that prove congruence. SSS, SAS, AAS, ASA, and HL. 4 of them we can use anytime we want. The 5th one we can use only on right triangles. These 2 do not prove congruence. You cannot write them as answers. Let's do some examples. I'm going to go really fast through this. We're going to try to spot what they are. Again, real fast. Mark the vertical angles. We have 2 sides and the included angle. This one's going to be SAS. So these are just some examples of ones we're going to be doing in class. Here we have angle, angle, included side. I don't have to mark anything. Angle, angle, included side. Good to go. This is a tough one. Number angles. I think it's easier to tell if you number the angles. But what do we know here? We know that we have a shared side. If we're writing a proof, we would say AC is congruent to AC. We would call that the reflexive property. That's when we do proofs. We're going to do that next time. But AC is congruent to AC, reflexive. Reflexive just tells the reader, hey, both triangles use this. Of course AC is congruent to AC. That's not up for debate by anybody. The reflexive piece tells the reader both triangles use that side, right? Like if this is 10, if this side is 10, don't both triangles have one side that's length 10? Yes, they do. So that counts as one of our S's. So we have an angle matching an angle. We have a shared side. And the other thing we have are parallel lines. We got to be so careful. Do not do this. What's wrong with that? What's wrong with that? Those lines aren't parallel. So we can't go 1 to 3. Can we go from 4 to 2? Yes. 4 starts on parallel. We turn. 2 ends on parallel. Nice. Those are parallel lines. Those angles are congruent. So what do we have here? I want you to look real hard, but the answer is actually AAS. And I know not everyone was thinking that. If you can't tell, please do this. Trace one of the triangles, not both, trace one. And sometimes it helps to even to draw it somewhere else. So, and then label the pieces. What are the pieces? We know that the top left has a match. We know that the bottom has a match. And we know that the shared side is a match. This is one triangle. Angle, angle, non-included side. So it's got to be AAS. What a lot of people do is they look at this, they see angle, side, angle, and they say ASA. But guys, that goes across triangles. You can't move across triangles. You've got to stay within the same triangle. All right, how about this one? Shared side, I'm going to go real quick. Right angle, if that's right, that's right. We have SAS, that's 2 sides and the included angle, SAS. Down here we have SSA, we have SSA. That is NEI. Don't you dare write that bad word. And then on this one, we have a shared side, right angle. Ooh, that's HL90. That's a right triangle. It's actually SSA, but the A is 90, which makes it HL. All right, guys. That's today's lesson. I know it was long. I know you loved it. See you next time. Boom.